Welcome back, Precalcsters. We just checked this assignment. Today, I'm going to give you guys a moment to get started. We don't have a super long lesson, but I say that without knowing for sure how long it's going to take. I don't have a ton to write. But I do want you guys to graph, and by making a table, so I'm just going to caveman talk. I want you to table and graph y equals the arc sine of x. Okay. There are a few different ways that you can build this table. If you remember when we did logs and we looked at the graph of a log, it was easier to think backward, to do the y and then see what x it gave us. I don't care how you do it. Other than when I actually write my table, I think the 3 columns will be helpful as we're trying to think this out. The y value it spits out. Okay, really important as we're looking at this. If I'm taking the arc sine of something, I get nice, lovely values to deal with. Now, when we're looking at that, remind me real quick, what was the domain of arc sine, if you check your notes? From where to where did we use arc sine? -1 to 1. Okay, as we're looking at this then, I would probably start at -1. And you can use super ugly numbers if you want, or just nice numbers, but I want you to construct this table for me and get a sketch of this graph. Cool, I'm gonna come around and take the homework. I'm gonna give you guys a couple minutes. Talk it out. Do you want to do the first point together before I say talk it out? Let's see it then. Okay, if I said the arc sine of 1, and I'm gonna have more work than I normally do. -1, sorry. Okay, if I'm trying to figure out what y value this enters, or gives me, do you agree that it's just, I can say y here? Like whatever it is, it's going to give me that value. If I take one step forward, and you probably won't have to do this with all of them, but what I'm really looking for is where, for which y, is the sine of y equal to -1. And I just took the sine of both sides and I changed it. This is the definition that we saw. Is there a place on the unit circle, some angle y, for -π/2 to π/2 where sine of y is -1? Say it again. Love the answer of 3π/2, except we're only working on -π/2 to π/2. Let's call it -π/2 instead. Now, there's very few times where I'd advocate for this. If I want to actually graph this, might it be nice to have a decimal? So 3.14 is what I have in my head, divided by 2, 1.57. Cool. -1.57. We just got the first ordered pair on the graph of arc sine. I want you to get me 4 to 7 more, depending on how ugly a numbers you want to use. I will give you guys a couple minutes, talk it out. Cool, cool, cool. All right, so here's our first one. Now, when I think about this, and I'm not going to jot this down just as I'm thinking. If I look for nice values of sine, and I start on the right half of my unit circle, -1 is straight down, right? And just so you can see it, so you don't have to just envision it or imagine it, here's my circle, right? So I start here and I say that's a nice y value. It's at -1, and I'm only writing the y values. Okay, I think that right here at -√3/2, I think that kind of sucks. But I think it's okay right here because I know I'm at -1/2. I then get to 0. I get to +1/2. And I get up to +1. Those are what I would consider the nice ones. I'm only looking at the y coordinates because we're looking at sine, right? And I'm on the right half of the circle because we've restricted to the right half of the circle. Okay, as we go through this, without having to reference our unit circle, we might get nice values. Can anybody tell me the angle in radians that gives me that 1/2? Or -1/2 rather. So π/6 gives me +1/2. -π/6. Now, I probably, personally, I would not do both columns of this. If I got to here, I'd be thinking, okay, well, what y value between -π/2 and +π/2, or the right side of the circle, gives me a -1/2, and you guys were able to tell me without showing the work. What y value would give me 0? 0. Cool. How about positive 1/2? Positive pi 6. And I'm skipping over this middle part, but I just want to emphasize, this is just saying, hey, what value of y gives me 0 on the right half of my circle? Okay, only one more. Last one is a positive 1 again, and that happens at pi halves, I believe. Cool, cool?
Yeah.
Baller. Now, we got to graph it with these 5 points. Anybody have more points than that? Okay, if you have a calculator handy, you can probably do your root 3 over 2 and root 2 over 2. You could get better points. But here's my challenge for you. I want you guys to graph this. That's it right off the bat. I know the x direction needs to run from -1 to 1, so I'll just pick out my scale here, -1 to 1. And the y direction goes up to pi halves. And in the negative direction, negative pi halves. I want you guys to graph this. I'm going to give you a moment, and then we'll come check it out together. Sorry, I blew up at you guys there. Looking at this, there's one little tiny thing that may be nitpicky, but that's okay. When I graph this, I'm going to try my best here. I see it runs through here to there, right? And I'm going to make that a little bit nicer. Oh, look at that curve. Gosh, dang, that was the best I've ever done. All right, and from this side, nope. Whew, look at that. Okay, here's the big deal. I can tell my graph isn't perfect. I want you guys to look really carefully. Anybody who I just screamed at mercilessly, you have something like this. I'm going to change color. I want you to tell me what's different about the graph that I've drawn and somebody's graph that does this. Like, it's obvious, I think. I kept going, right? Now, remember that this is a part of a wave. If we didn't restrict our domain, this is the rest of the shape that we would see. It is my sine function just turned or reflected. Why can't I go anywhere beyond that red? It fails a vertical line test, and we no longer have a function. When you were looking at this, the big yelling part that I did, you better not extend beyond wherever you restricted your domain. You can't pass it, because if you do, your function breaks, and now it doesn't make sense to talk about this function that's not a function anymore. Cool. This idea hopefully feels okay to look at it. What I stressed with Mickey a moment ago, and I'm trying to remember the way. Did I call you Kalisha a minute ago?
During first period, yeah.
My bad to you, not because it's a negative thing, but just my mistake. Notice, all that happens is we just think backward. If we think about sine, if I tell you to look at your unit circle and tell me the sine of pi fourths, what is it? What is the sine of pi fourths? Root 2 over 2, which means in my mind I'm thinking on the graph of sine, pi fourths comma root 2 over 2 is a point, right? To get the inverse, I just switch it. Root 2 over 2, plug that into arcsine, and it better spit out pi fourths at us. The order, it just switches. Now, if you are interested, I can have you guys do the same thing for arc cosine and arc tangent. Or we can just look at them on a Desmos, and I can say, hey, if you need to adjust these, you can. Do you want to draw the graphs or just see them? I'm not going to make you graph them on your own, just so you know, on a test, on a quiz. Let's just look at them, and then if you're just dying to have more graphs with tables in your notes, leave space to add them. So here we are on Desmos. So here's the graph of sine that we still have from yesterday, and I'm going to graph the arcsine. And we're going to turn it on so we can see it. Okay, there's a graph of sine that we've restricted. Here's a graph of arcsine. Look at that. Does it look like what we just graphed? If I continued this going, would it just turn into the sine wave just doing its regular thing? Yes. Cool. Do you guys watch Rick and Morty? Have you all seen, I know, yeah. Have you guys seen the episode where Jerry's in the simulation, he's too dumb to realize it? And he just keeps being successful because no matter what he says, they just go, yeah. Yes. Can we make it a deal that if I ask a dumb yes or no question, you guys give me the Jerry version of the answer? Does that sound good?
Yes.
Yes. Cool. All right. So there's arc sine. Let's get crazy. I want arc cosine this time. And we're off. Look at that. It runs from 0 all the way up to pi, I would assume it is, because that's the domain that we restricted. And I can see it. It does the same thing. It's just a wave the other direction. Now, that's really not that crazy, right? Compared to arc sine, like, oops. I wonder if it does this. Not that one. You think it's going to do it? Hey, it knows what I'm doing. Neat. Okay, so here we have arc cosine. Here's arc sine. Guesses on tangent or arctangent? What's the range of regular tangent? How low to how high? All of them, right? All real numbers. So what should the domain of the arctangent be? Check it out. It looks almost loggy. Now, turns out there's a reason for this. This certainly looks like a logarithmic function to me, with the second asymptote missing the vertical asymptote, but that's all right. These graphs, we can think about in the exact same way. If you've not done so yet, you should, very much should, add the tangents to your unit circle. Cool. I'm not going to make you guys graph those anymore. If anybody wants to, I would encourage you to do it, but here's how we get them. Cool, cool? Sweet. All right, so let's get into the heavy lifting with these things then. So we need an actual reason for these. And today's essentially just all examples, just so you guys are aware. If I want to use inverse trig or regular trig, I want to make sure that we can distinguish the difference between them. This is going to be a big star warning. Actually, you know what, feels kind of grassy. Cool. Here is a grassy statement that we need to make sure that we have somewhere. Okay. Grassy as in I just make sure that you have it. We use SOHCAHTOA, which is trig, but it's SOHCAHTOA, if we know sides, if we know an angle, sorry, and a side. And specifically, I'm going to let you guys catch up, but if we use SOHCAHTOA and I have an angle that's a given angle, like I know the number, and I know a side, I can then find the length of another side. Do you guys agree with that? So SOHCAHTOA if we know an angle and a side, to find another side. There's nothing new out of this. SOHCAHTOA gets used to find the side of a triangle. Now, when we flip it, would you rather I say inverse SOHCAHTOA or arc SOHCAHTOA? Inverse SOHCAHTOA, I'm good with that. Inverse SOHCAHTOA. We use that if we know two sides. If we know sides, to find, and what does our arc function spit out at us? I plug in the sides, and then I arc trig it, and it gives me the what? I think I heard it. Say it again. The angle. And I see that happening on this table that we just did. I plug in a ratio of the sides right here, and it spits out the angle in radians at me. This is all that it's doing. So to find an angle. Now, I'm going to say one, maybe two examples of what's going to look like a problem from geometry, because you guys saw SOHCAHTOA in geometry for the first time. So here we go. Trigonometry is what color in your head? Green for you? It's yellow for me, but I can't write yellow up here on the board nicely. We use that color green. So example. And we're just going to say, how do we want to word this example? Ooh. We're just going to call this geometry, because this is like old school stuff. We'll do one of this type. I'm going to draw us a right triangle. And I don't know anything about this right triangle, but you guys are going to hook it up. I want you to find theta. And here is a lovely right triangle doing its thing. And let's say there's a right angle, and we'll use theta up here. Okay, there is not a right or a wrong answer for this first one. Sean, give me a side length. I don't care which one. Just tell me vertical, horizontal, or diagonal. Vertical has a length of 2. Awesome. Barsega, another side. I don't care which one. And what's the side length here? 4. Awesome. I don't know this one. I'm going to call it X. Could you find it? How, Abigail? You could Pythagorean theorem this and get it. Do I ask you to find it? Not X, right? We want theta. I want you at your desk to determine which trig function should we use, and should it be inverse or the original. I'm going to give you a moment. Find me theta. Let's go to the nearest 10,000th, which just means 4 decimal points. Don't move your decimal point. Just use 4 decimal points. Cool. I'll give you a second. As you're looking at it, there's 2 ways you might go through this problem. Why tangent, I guess, first of all? From this angle theta, I have the opposite and the adjacent. Okay, 2 ways we can do this. In my mind, depending on how comfortable you guys are with this, in the geometry standpoint, you would first write that the tangent of theta is equal to, what's the opposite? Over adjacent? 2. This is how you would do this in geometry. And then you would go one step further, and I'm going to switch colors only to show this is where I would start in with this problem, understanding that we're like an actual trig. To solve for theta, you do what to each side? You just take the arctangent. As soon as you realize it was tangent, but you're solving for an angle, just jump right to arctan. I'm going to say it's the arctan of 2. I have no idea what this is, but you guys are going to tell me. So I hear 63.4 and a huge important distinction. I'm pretty confident that this is degrees. I'm pretty sure of it. Make sure it's included. I said 4 decimals, so can you go a little bit further? 4359? 49. 4349 degrees. Awesome.
Why did you choose 2? You just chose.
What's 4 over 2? Yep, I just simplified. Cool. Y'all remember doing those from geometry. Okay. You may have to do another one, but we're going to switch gears a little bit, okay? Now, looking at this, we have, my guess is 15 minutes or so. We have a couple more things that we can do. And right off the bat, it will be our last main section of this, but we're going to look at compositions. Now, composing trig. There's 3 of these compositions that I don't think we need to write, but as long as your ears are open and your minds are open, we should be all right here. What's this? If I take the sine of the arcsine of x, the sine, and I'm going to write it, but I don't think you need to. The sine of the arcsine of x is x. That's always going to happen, right? Because function and inverse function undo each other. Would it change if I did it with cosine? What's the arc cosine of the cosine of x? X. What is the arctangent of the tangent of y? It's y. I don't need to write those down. Those are identities. They're given to us in the definition of our inverse trig stuff. Okay. What's a more interesting question is maybe, just maybe, we can make them a little bit crazier. So let's do example. And instead of just doing the sine of the arcsine, which is nah, let's mix compositions. Now, for these, I'm going to be looking for an exact value. And I'm just going to specify that here. The way that your book words these problems is it says find the exact value for each of the following compositions. Deal. All right, here we go. First one we're going to do together, and hopefully you guys will kind of push me through. What's your favorite trig function, Sean? You like the tangent? Okay. Let's find the tangent of the arc cosine, ooh boy, of 2/3. Love it. Do these undo each other? No. Now, Fern, I like what you're doing because you're going to give me an answer in degrees, but you're going to give me an approximate answer, which is not quite what I want. That's okay. It's a good check. Like, valuable. Do you get a number?
Yeah.
What is it? 1.118. All right. So, we need to figure this out. First off, we're going to start front loading. You'll hear me say this again in another class if you take another class with me. What's the inside function? Everybody okay with arc cos is the inside? And then inside of that is 2/3, right? So we have like a nesting going on here. Remind me real quick, this thing spits out a what? If I ask you for the arc cosine of something, it's going to give me it's going to be a number, but what does that number mean? Is it a side ratio or is it an angle if I take the arc cosine of something? This is an angle. This is, I'm going to say theta for our shorthand. Which means if I could find whatever angle this was, I could then take the tangent of that angle. Everybody on board with that? So let's deal with this. We're going to use a little bit of substitution for just a really quick moment. Do you guys agree that the following expression looks nicer? I prefer to think about the tangent of u. Does that look easier to deal with? I think we can probably all agree. Hold on. That's an obvious yes or no. Is that easier to deal with? Yes. Okay. What's u representing this? Okay. It probably feels like I'm just kind of rearranging, but we're just substituting right now, yeah? So silly. I'm not going to make you guys do it every time because your fingers are going to get tired from snapping. Okay. Anybody in here like really awesome about thinking about arc cosines? Are you? I'm not. Like I can think about them, but if you say, oh, u is the arc cos of 2/3, I don't have it in my head yet. What's easier than an arc cos to think about? What does this imply? If u is equal to the arc cosine of 2/3, then immediately this piece implies something else. And I'm just going to do it here. Don't use theta. What's the cosine of u must be equal to 2/3. Kind of. It's because we wrote u here. I could have written any letter here. That was arbitrary. But as soon as I write u is equal to the arc cos, I can rearrange it to think in cosines. Everybody cool with that? Okay. Remind me now, we have some angle u currently. And it winds up, it's the exact same angle that shows up as theta up above. I just changed the lettering. Could you draw me a triangle with an angle u such that the cosine is 2/3? And that feels like quite the chain. What is cosine with SOHCAHTOA? So I know that the adjacent has a length of 2 and the hypotenuse has a length of 3. Everybody good with that? Okay, and it was positive, and if I'm dealing with arc cosine, I must be in quadrant 1. And that's me thinking top of the circle with arc cosine. All right, so it's a quadrant 1 triangle. Cha, cha. Not to scale at all because I don't care. Quadrant 1 triangles have this angle u that forms them. Again, I'm using u because this is what we've written here. From this angle u, what is the length of the adjacent side? 2. And the hypotenuse? 3. And with a little bit of Pythagorean theorem, I think you're going to find root 5. 3 squared minus 4 is 5 and 6 square root. Yep. Okay. Now that we have this triangle drawn, and what seemed like a kind of complex problem, in my opinion, maybe not yours, could you tell me the tangent of u? Now, with this triangle in mind, the tangent of that u that we just found and we've expressed, how do you find tangent? And what's the opposite length? Over what's the adjacent length? And we can do it. We can compose these by making sure that we see exactly what does this represent. If you're comfortable with the arc cosine as an angle, and you can draw a triangle. You can do these problems. I want you to do one more for me, and then I think we're about done. Oh no. Okay. On B, I'm going to catch up to you guys. I want you to evaluate for me the cosine of the arc sine of negative 3/5. The cosine of the arc sine of negative 3/5. Cool, and I'm going to find a spot to make that fit on my page. If you're watching this video on the road, my tip that I'm going to give everybody is where this lives. Arc sine, which part of the circle are you thinking of? It's either top or right. Those are the only options. So which side's the negative part of the circle?
If that was gonna ask if it was negative 3/5.
It is negative 3/5, yes. Okay, repeat after me. Arc sine, right side. Right side of the circle. Which means arc cosine is the top. Okay, if you can just get those.
Why not how do you know that it has to be the top and side?
Because if you look back at arc sine, recognize that we restricted the domain from negative pi halves to pi halves, which if you look at the unit circle, that's only the right side. Negative pi halves all the way to pi halves. Okay, cool. I'm going to give you guys a second. This is a quadrant 4 triangle, is how it should be drawn. Quadrant 4 based on this. Cool. I'll give you all a minute. Must be remembering a joke I told at one time. So, here we are. I'm going to jump a little bit further ahead. I'm going to use what as a placeholder for this? I'm going to use u, and then as I'm looking ahead, I think using the same strategy right off the bat, I have that the sine of angle u is equal to negative 3/5. Okay, so if I think about the right half of my unit circle, because that's where sine is restricted when we think about it, am I in quadrant 1 or quadrant 4? I'm in quadrant 4. So here is the hypotenuse shooting down to quadrant 4. Bow ties and butterflies, should I go up or over? Up in quadrant 4. Check it out. Here, Sean, before you erase, I want you to check your answer. There's our U. Cool, it's our central angle formed there. The way you draw the triangle is going to help keep stuff straight. It is not going to be guaranteed that your answer is correct. Okay, it will help though. From this angle U, what is the opposite side? So negative 3, which means this is 5, because that's hypotenuse. And then this certainly looks like a Pythagorean triple. I think it's 4. As soon as we get this triangle drawn for U, this question is just as easy as deciding what is a cosine of U for this. Adjacent is 4, hypotenuse is 5, and we're done. Okay, there is one example I would encourage you to look at, but I'm not going to test you on it here. In your book from time to time, and we'll work out the assignment, you'll see it on occasional homework stuff, but you'll also see it in the notes. This example number 7, I think that you should look at. You don't have to write it down in your notes, but you should read through it and try to follow what they're doing. The technique that they're doing, this symbol, this red S looking thing, we have Gottfried Leibniz to thank. That's for the summa, or the integral is what it's called. This technique in calculus, where we have this ugly thing, they can write it as an expression in terms of x. I would encourage you to look through this example, see if you can follow it. We will see that again, but it's not going to be our focus today. Cool. All right. You guys get 15 minutes, and let's figure out what we gonna do. I'm going to have to get a book that doesn't have answers in it. I want us to do homework, and I'm going to put it down here real bold, real fast. Okay, let's check it. Homework 4.7.2, which you will find starting on page 326 again. And I would like you guys to do problems 41, 46, oh, I love it, 57 through 61. I'm okay with that. Cool. 14 minutes right now. I will get these up. I got to make sure that none of them show. 41 and 46. Awesome. So I'm going to use a little editing magic and I'll put these up on the screen. There is the assignment. Awesome. Have fun. Oh, awesome news. We only have one section left. Yes. I'm gonna let this go for a second so the video doesn't abruptly end with like a half a second of showing that.